Good morning. I'm Altaf Hussain, a former professor, Department of Chemistry, University of Dhaka, Bangladesh. We are preparing a series of lecture of AS and A-level chemistry. This is the 33rd lecture on analytical techniques. In AS level, the third paper is on analysis, and in A level, the fifth paper is on analysis. In the analysis, we have to know different techniques of analysis. So we start with the AS level third paper analysis syllabus. And I have to mention that almost all chemists need to know the qualitative and quantitative analysis. All chemists, there is no way out that you become a graduate of chemistry without doing qualitative and quantitative chemical analysis. So you need some different chemicals and glassware to perform this analysis. Chemical analysis is cheaper compared to instrumental analysis, but it is essential to know the different chemical reactions and about the compositions and structure of different chemical compounds. Yes, we know very well now the modern chemistry, we use instrumental techniques to analyze natural and synthetic compounds. But you see, the instrumental techniques means there are some instruments which you use to analyze these, natural and synthetic compounds. What are those instruments? For example, mass spectrophotometry, UV visible, and IR spectrophotometry, diffraction techniques such as gas chromatograph, HPLC, and NMR, etc. There are many other instruments. One can use instruments and analyze the synthetic and natural compounds very quickly, no doubt about it. But this will never replace the so-called chemical analysis we do simply with glassware and so. Instruments are very expensive, definitely, but these one can analyze very quickly, and then it is accurate also. In classical chemical analysis, we destroy the sample by reacting with other chemicals. But in instrumental analysis, in very many cases, we need very small sample, and as well as we see that the samples are not destroyed during the analysis. In AS level, we will see that there are only two instrument analyses in the syllabus. One is mass spectrophotometry, and another is IR spectrometry. Okay, in our earlier lectures, specifically when we are talking about atomic structure and bonding, we did talk about mass spectrophotometer to determine the isotopes of elements. And we took it in other details. But here we will see that we need to know the relative atomic masses of a unknown molecular compound, and specifically we use this very much in organic compounds. This technique, mass spectrophotometry, is very extremely sensitive and requires very small samples, and we mean the small sample, the nanogram level. We have to have a very high vacuum inside the mass spectrophotometer, because we will produce their molecular ions and fragments of molecules to keep this fragment of molecules and molecular ions. So we have to keep the instrument in such a way that it should not react with other compounds or elements. Okay. Excuse me. Okay. Here it is a schematic diagram. What happens in what we have already discussed in earlier lecture at the beginning during atomic structure and bonding. So what we do in mass spectrophotometer, high speed electron bombards the molecules, high speed electrons, which is bombarding the molecule, and then we get molecular ion. And this molecular ion, what happens? That due to electric and magnetic fields, it goes to where we can record this molecular ion in a detector and then analyze this. So what this turns into ions, here it is, turns into ions by knocking out one or more electrons. Bombarding molecules, high energy electron not only ionizes but also split them into fragments. Molecules, what happens? Then a fragmentation pattern, we get also fragmentation pattern from this mass spectrophotometry. Molecules reacts to more readily at weak bonds and at bonds with high, more stable fragments. It turns out that positive ions with the charge on secondary or tertiary carbon atoms are more stable than the ions with a charge on the primary atoms. So such as these species are more stable than this double bond in which breaks. Okay, after ionization of fragments, the charged species are accelerated, as I say, and deflected by electric and magnetic fields. This deflection depends on mass to charge ratio of the molecular ion or fragment. Mass to charge ratio is represented like this, and then Z is equal to 1, 2, and so on. But in A level mass spectrophotometry, we will meet all example with Z is equal to 1. Okay, here we have a schematic diagram at the molecule M1, M2 in a mixture, and then you see that we bombard it with high-speed electron and then ionize it. And there it is the ionization, and where one of the molecule in this mixture has been ionized, this is M2, and then we can take a more electron from here, and then we get fragmentation of this. So, and then M1 class, which is positively charged, and then this is detected by a detector, but a neutral one will not be detected by detector. Well, the positive ions then finally reach the detector, as I said, and there will cause a small current. With this, then this current is amplified and the signal is fed to a computer. And then we can print it in a print diagram, and then this spectrometer often output is often presented as stick diagram, as you say, here is stick diagram. And this X is mass to charge ratio, that M by Z. This is a relative abundance, percentage of relative abundance, you see. Okay. So, so what happened? So when we get it, we will see the highest mass to charge ratio is the molecular ion in the sample, which has been injected to mass spectrophotometer, and that is called parent ion. And this one gives us the relative molecular mass of the compound. Okay. The spectrum, here you see that there are two peaks almost equal in abundance. There are two peaks. What are these two peaks? Why these are two peaks here? It is because we know bromine naturally gives two isotopes, bromine 79 and bromine 81. And this bromomethane, where there is bromine, both isotopes are there because it is naturally occurring. So therefore, we get two molecular peak, one for bromine 79, that is C2H5Br 79 plus, one for this and another for 81. That's shows in the peak here. Okay, then what happens when it is fragmented? Because the first is bond, carbon-bromine bond is break down. And therefore we get a fragment like this, C2H5 plus. And C2H5 plus, its mass by charge ratio is 29. You see, here is a 29. And similarly, if we continue this, then we get loss of hydrogen, and then we get mass by charge ratio 28 for this C2H4 plus, and for mass by charge ratio for this C2H3. So that are the fragmentation of bromoethane in mass spectrophotometry. What happens then? This gives us the inside knowledge of the structure. And then if we can identify the fragments, we can piece this together and give a likely structure. But that is always not true. We have to have other techniques, and especially with the help of IR, we can confirm this structure. So this is what is what happens. Okay, here are two problems for mass spectrophotometer diagram. The right one is mass spectrophotometer C5H10O2. What is C5H10O2? So one is ethyl propionate, and we can also have methyl butanoate. So these are two isomers, and then using mass spectrometer, can we identify the isomers? Can we say which isomer is responsible for this mass spectra? Well, we can probably do that, because if you see this one and this one, its molecular mass, you get 102. Both has got molecular mass 102. That means both isomer of C5H10 has got molecular mass 102. So with this peak, molecular mass 102, we cannot identify this. But when we fragment this, we will see that this is possible to say that's whether it is C5H21, which isomer it is, whether it is a ethyl propanoate or methyl butanoate, that we can say. The other main peaks here is, one is M by Z is 57, another M by Z is 29. This is 57P and this is 29P. We can see. Now we start looking for the fragments. The fragments, these and these, by breaking the carbon-carbon double bond and carbon adjacent to carbon oxygen double, carbon-carbon single bond and adjacent to carbon oxygen double bond, which correspond to this mass spectrum M by Z, 57 and 29 respectively. But if we take butanoate, then we see that mass charge ratio of the possible fragmentation for butanoate. This is one of the fragmentation, and this is another fragmentation. So mass by charge ratio value is 71 and 43. We can see that there is no fragmenting mass by charge in 71 main spectrum, and also not 43. Therefore, it is proved that this is not a methyl butanoate, but it is an ethyl propanoate. This is one problem. The second problem is this, that we get a mass spectrum of butane, and it is in left. There are some questions. Giving this mass spectrum, there are some questions. What are the questions? One, what is the peak? The mass spectrum of butanoate correspond to the molecular ion. We know the molecular ion of butane is this. Molecular ion of butane is this. If we take the mass of molecular ion of butane of this, we say it is 59. So here it is, S is the molecular ion of butanate. Okay, then it is said what is the relative mass of this arm, that is M by Z. What is M by Z? Is 58. We get it in 58. Okay, then what suggests the identity of the fragments labeled as P, Q, and R. So this is P. So this P shows CH3 plus. M by Z is 15. Q, that is Q. It is M by Z is 29, and it is CH3, CH2 plus. And R, here it is R. This M by Z of R is 43. The CH3, CH2, CH plus. So we can identify this as RPQ. Okay. It is C suggests a reason why P at M by Z 15 is relatively weak. We said abundance in the molecular fragmentation and also molecular ions, percent advantage. This percent advantage is very low, 15, very low. And therefore, that means CH3 plus is very low compared to other fragmentation in the mixture. So therefore it's very weak. Okay. We use symbols to show one way in which the parent is fragmented, butane group fragments. We showed it like this. This is the possible way of fragmentation on the parent ion, molecular ion. Well, this is about mass spectrometry result. You will get many problems in your textbook, and that is very easy to solve. I hope you will do it at home and find out that that's not difficult. Now we say that we need to go for other technical instrument techniques to confirm this, and we said it is often we use the IR spectrometry. And what is IR spectrometry and what is spectroscopy for that one? The spectroscopy were practical techniques. What for? Because we can study the composition, structure, and bonding in compounds. But this is regularly used by chemists in qualitative and quantitative measurements. Okay, depending on the electromagnetic radiation, you can have these instruments called spectroscopy and IR spectroscopy, visible spectroscopy, and UV visible spectrophotometers. So IR spectroscopy is an analytical technique used to identify functional groups in organic molecules. The functional group we can also use by mass spectrophotometry, but we can complementary this technique is also used to confirm it. We also know that all organic molecules absorb radiation in the infrared range of wavelengths. We would restrict our discussion, therefore, with IR spectroscopy while we are discussing the AS level chemistry. Infrared radiation from glowing a lamp or fireworks was warm, and this because infrared frequencies correspond to the natural frequency of vibrating atoms or molecules. Our skin warms up with the molecules absorb infrared and vibrate faster. That's why feel warm when we put infrared ray in some of our parts of our body. Okay. How this instrument looks like? This is a very schematic diagram. If we are showing a single beam spectrophotometer, very, very schematic. Radiation source, sample, and then you detect it, then you send it to computer and print it. That's what it is. Spectrometer absorbs infrared radiation at wavelength, which correspond to natural frequency at which vibrating bonds, vibrate the bonds in molecules at band shape or stretching shape. However, these molecules that change their polarity we have been talking about polar molecules. So when we have a source of radiation, and this due to this radiation, if this molecule changes polarity, we can only detect those molecules by infrared spectrophotometer. And how we do it? The spectrum is plotted against transmission against wave number. We can go for you said vibrating the molecules. Here you say it's a polar molecule, vibrates, and therefore there is a polarity development, and that's why we get this infrared active, this molecule. This one is a band shape, this is a stretching shape, this is a band shape. Here also in polar molecule, we get the infrared active species. Here, this is a symmetrical stretch of carbon dioxide molecules, and there is no change in dipole. Therefore, this way we cannot detect carbon molecule in IR absorption. So IR is not applicable for this one, but it is not a symmetrical stretching of carbon dioxide molecule. It's an asymmetrical stretching, and that's the net dipole changes. And as net dipole changes is created, it is IR is absorbed here. So it's an example in which molecule IR will not absorb, in which molecule IR will absorb. So remember that we have to have net dipole changes of the molecule to get IR change, IR absorbed. We can come to where I said about the spectrum we get in a IR spectrum, where this y-axis is absorbs, percentage of absorption, and here it is the wave number of the measured wave number. So you can see this is, and one more thing that the both scale is going to lower values here and lower values here. You have to remember that. So energy bond corresponds to that, so we said. And one thing we say that the unit we used for wave numbers is centimeter inverse. So centimeter inverse, and the absorption percentage. So you see, in some cases we get the two specific characteristic absorption. For example, here we have a ethylamine, and the amine group absorbed from you see from 3,300 to 3,500. So this is a broad peak. We'll talk about broad peak and sharp peak in the next slide. And I suppose we have been talking around 20 minutes for this analytical technique. We will take these slides for next lecture, as well as the rest of the topic in next lecture. Thank you very much for listening up to this AS level analytical techniques. We'll continue it in the next lecture. Thank you once again.